State of charge estimation methods. Effectively estimating the state of charge of the battery and involving it into the vehicle control is very important in collecting the battery information, optimizing the vehicle operation, driving experience, enhancing the utilization rate of battery capacity and energy, preventing battery from overcharging, over discharging, and finally ensure the safety and service during the use of the battery. State of energy is the another term which analyzes the remaining capacity from the viewpoint of energy and in terms of usage. It can build up a simple relation between the remaining capacity and the time of use or running distance of the electric vehicles. In actual use, the main function of the battery is to store and release the energy. The running distance and endurance time of the electric vehicle are directly related to the quantity of energy released by the battery. Hence, state of charge and the state of battery from the viewpoint of energy is having the more practical significance. The SoC or state of charge refers to the remaining capacity as a percentage of the maximum available capacity. So state of charge is how much is the charge remaining and how much is the maximum capacity into 100. Remaining capacity of the battery as it discharges from the present state to the fully discharged state. The maximum available capacity is the capacity of the battery as it discharges at low current from the full state to the fully discharged state. Fully discharged state, the OCV of the battery discharges to the state of end of discharge voltage. Thus, SOC is equal to 0%. That is fully discharged battery. In full SOC, when the OCV reaches the EOC voltage, thus SOC is equal to 100%. The various methods of SOC estimations. The first one is the load voltage detection method. During the discharging process of the battery, when the load current is stable, the change in load voltage with SOC is similar to that of the OCV with state of charge. So we can use the load voltage to estimate the state of charge. The load voltage curve of lithium-ion battery at different discharge rate is shown in figures. The advantage of this method is that when discharging with the constant current, real-time estimation of state of charge batteries is realized effectively. In practical application, the fluctuating voltage of batteries makes load voltage detection method a difficult one. To solve this problem, it is necessary to store a huge amount of voltage data and build a mathematical model of the dynamic load voltage with state of charge, current, and temperature. The load voltage detection is not commonly used in real vehicles, but often used to judge the cutoff batteries during the charge or discharge. Electromotive force method of the state of charge. In practice, the OCV of the battery, as shown here, in the, is often used to approximate the electromotive force, that is the open circuit voltage. The open circuit voltage of a lithium ion battery has an approximately linear relationship with state of charge and does not change with the battery running conditions. Thus, the relation can be used to estimate the state of charge. The changes that the open circuit voltage of a lithium manganese oxide battery undergoes with the state of charge is shown in the above figure. However, the acquisition of the open circuit voltage requires that the batteries stand for a long time and are stable, especially under conditions of low temperature and high rate. The estimation of SoC based on the open circuit voltage can be using lookup tables and mathematical expressions. So, electromotive force method or the open circuit voltage method can be noted and a table can be formed, and for a particular voltage level we can note the state of charge and that can be used or using the mathematical expressions. The another method of SOC estimation is a resistance method. The internal resistance of battery can be classified into internal impedance and resistance, both of which are closely related to the state of charge. By using electrochemical impedance spectroscopy, that is the EIS method, and the relationship between each electrical parameter of the equivalent circuit model and the SOC, the state of charge can be estimated according to the equivalent circuit model parameter of the battery. However, the resistance method is rarely used as the AC impedance is greatly affected by the temperature, and there is some dispute about whether the measurement of AC impedance should be made in the balance state of the battery or in the charge discharge process. The next method of state of charge estimation is ampere hour counting method. The ampere hour counting method is simple, reliable, easy to use, and commonly used approach for the estimation of the state of charge of the battery. If the original state of charge or discharge is SOC 0, then the current state is calculated as SOC at the end or at the particular event is equal to SOC 0, that is initial state of charge, plus delta Q, that is the capacitance change from the initial state to the current state, that is the charge, change into the charge, divided by the Q max, that is the maximum charge. And that is can be again equated as SOC, that is state of charge 0, plus integration of IDT from SOC 0 to SOC end. The SOC end is the final state of charge, divided by the Q max, that is the maximum charge. According to the definition of SOC, the maximum available capacity of the battery, Q max, can be also calculated as Q max is equal to delta Q divided by SOC 2 minus the SOC 1, that is the SOC minus the earlier SOC, and that is equal to integration IDT over T1 to T2 divided by SOC difference. The ampere hour counting method can be applied to the batteries of all electric vehicles if the current measurement is accurate and data of the initial state is sufficient. Then it is definitely a simple and reliable way for the estimation of state of charge. The ampere hour integral cannot solve problems such as accumulative errors self-discharging capacity loss, and the changes in the maximum available capacity. So there may be certain errors because of the self-discharge and errors. With the usage time increasing, the estimation error of SOC will gradually increase. So over a period of time, there will be increase in the SOC errors. So it is important to revise SOC 0 regularly. That is the initial state of charge of the battery has to be checked. To obtain VOCO, VOCV, and then take the advantage of SOC open circuit voltage to obtain the new SOC 0. This is the way we can modify the SOC, initial SOC. The next method of SOC estimation is the Kalman filter method. The Kalman filter method uses a state space method to describe the system. The solution is calculated by a recursive method, and it has a self-adaptability. For a linear system, the Kalman filter is gradually stable. For the nonlinear characteristics of a power battery, the Taylor formula is used for linearization, followed by calculation by the Kalman recursive method. This is known as extended Kalman filter method, that is the EKF. Kalman filtering method algorithm equation can be divided into two parts: predict system status, system output and error, and second, correct the current state estimate value based on system output value. When the system state equation is nonlinear, Kalman filtering method cannot be put into use directly. This system equation discretization is required, and this kind of nonlinear equation for discretization of Kalman filtering method is called as the extended Kalman filtering method. So to estimate the SOC through the extended Kalman filter, first build an appropriate battery equivalent circuit model, generally a circuit model, that is equivalent model. Then recognize the circuit by using the experimental data of complex pulse and build the state equation and observation equation of the circuit model by selecting a suitable state variable. Finally, estimate and filter the state of charge by Kalman filter method. So here Thevenin's battery model is shown, where I represent the charging and discharging current, V0 represent the battery terminal voltage, VB the battery voltage, and R and D are the equivalent branches of the battery. The Thevenin's dynamic circuit model includes the battery open circuit voltage VD, the battery terminal resistance R, the ohmic resistance Ri, and electrochemical polarization resistance RD as shown here. The equivalent capacitance CD is to describe the cell electrochemical polarization and concentration polarization, which reflects the battery transient response during the charging and discharging process. According to the Kirchhoff's voltage and current law and capacitance voltage variation and its current relationship, Thevenin circuit model of the state space equations are expressed. So that is a V dot B is equal to 1 upon CB. Again, the V dot D is equal to minus I upon RDCD into VD plus 1 upon CD into I. So writing this Kirchhoff's voltage and current equations. So V0 is equal to VB plus VD plus I into RI. So this is the drop across this. plus VD and drop across this VB. So these are added. The relationship open circuit voltage and SoC of lithium-ion battery is not linear. Drawing the curve graph based on the measurement data, the open circuit voltage function relation about SoC can be obtained, and that is VB equal to A into SoC plus D. Based on the equations, the system equations are derived in the state space form. So SoC and VD that is equal to the matrix I upon K CB and second minus I upon RDCD into VD plus 1 upon CD into I. So V0 is calculated based on the K into SoC plus VD plus I into RI plus D. These two equations are state equations and observation equations for lithium-ion battery model. Discretization for continuous equation and SoC calculations can be done by extended Kalman filter method. The next state of charge estimation method is the neural network method. As a battery is highly nonlinear system and it is hard to build an exact mathematical model of the process of charging and discharging. The neural network has basic nonlinear character, parallel structure, and learning ability. So reacting to external excitation, it can give out corresponding output and can simulate the dynamic characteristics of the battery to estimate the state of charge. The neural network model includes a feed-forward network and feedback network, and the theory of an error backpropagation neural network is the most developed and widely applied network. The neural network structure based on the model of battery SOC estimation is shown in the next slide. We'll see that. The typical neural network with three layers are usually used to estimate the battery's state of charge. Number of input and output layer is confirmed by practical problems, generally a linear function. The neuron number of the middle layer depends on the problem complexity and analysis precision. The input variables for the battery SOC estimation include voltage, current, accumulated releasing electricity, temperature, resistance, and environmental conditions. So is the neural network where there is an input layer, middle one is the hidden layer, and last one is the output layer. The choice or the number of input variables of the neural network is directly influence the accuracy of the model and calculation. A neural network can be applied to all kinds of batteries, but the disadvantage is that the large amount of reference data is required for training the neural network, and estimation error is affected by the training data and training method. So this is all about the state of charge estimation methods. The next is the basic requirements of EV and PHEV batteries. This is another point. The basic preferred characteristics of plug-in hybrid electric vehicles batteries can be summarized as they should have high specific energy, which results in higher all-electric range and less recharge cycles. Second, high specific power that results in high acceleration characteristics of the PHEV due to high rates of currents available from the battery without causing any permanent damage to the battery pack. Third, high number of charge discharge cycles available and high safety mechanism built into the battery because of high power rating of the battery packs. Next is the environment friendly aspect of the battery that is being recyclable and including low amount of toxic metals. So the battery should be an environment friendly battery.